In this video, I'm going to discuss constructing basic derivations and how to use the program in doing so. So we'll be discussing both the rules for forming, we talked about inference rules, but we have a whole derivation system which the inference rules sit inside of, and so we need to start learning about the system in which they sit inside of, and also how we use the program to construct derivations. So we're going to start with an example argument. So our argument is going to have the premise P, the premise if P then Q, and the premise if R then not Q, and the conclusion is going to be not R. These three dots there, like that, they mean because, or, sorry, they don't mean because, they mean so or therefore, and they flag the conclusion. Okay, so let's go and take a look at a derivation inside the derivation system. So here's the derivation. And if we look at here, this is the argument we're being asked to derive. And so we have P period, if P then Q period, if R then not Q, the three dots, and then not R. So those periods there, they separate the premises from one another. And again, the three dots, the so or therefore symbol, separates the premises from the conclusion. So here we have what we're being asked to derive, and again, it's just repeated. So the first thing you want to do is hit enter. Now we have three columns here. The first column is a number column. We'll see what happens in this, and what happens in the rest of the columns. So on the very first line of every derivation, you need to write show and then the conclusion. And that's the first line of every derivation, is show and then whatever the conclusion is. This column, so the number column, this is the formula column, and here we're saying show, not R, and then this is the justification column. Now here, it's blank. Why is that? There is no justification for writing show. Writing show just means I intend to show something or other, and you can intend to show or try to show whatever you want. It doesn't need a justification. So now the next thing we want to do is to put our premises into the derivation, so we can copy. Now if we just hit enter and we check it, so here this says it's incomplete, that's correct. This says not yet canceled. That's because the conclusion of a derivation is canceling that initial show line, and so this is telling us you're not done yet, you haven't canceled it yet. That's fine, we don't think we are, no problem. But now this says no justification given, and that's a problem. Each line besides a show line does need a justification. So the justification for this is PR for premise. Oh, actually, sorry. And if we now check it, that got all messed up. That's better. Okay, now let's check it. Good. So now we have here the first premise. We have here the justification PR for premise. And here, when we check it, it says just fine. Now let's go to the next line. Now, we want to use we're going to need to use all of our premises. None of the derivations or arguments you're asked to do derivations for have extraneous premises. Always the premises are, use of each premise is required. So one nice thing about the program is that you don't actually have to write this stuff out because we have something called command mode. In command mode, when you enter the justification and then hit enter, it will give you whatever is justified by that justification. Now there are three things that are justified by PR because there are three premises. So let's put in the second premise. Okay, there we go. So we put in PR here, we hit enter, and it asks us what did we want to put in. Now we can be a little bit quicker because we know which premise it is that we want to enter now. There are three premises. There's P we have on a line. There's if P then Q we have on a line. But we want to use a third premise too. So we'll say PR3 and hit enter, and now our third premise is put in. So good. Okay. We've now entered all the premises. So that's, in the simplest form of a derivation, the first thing you do is you put in show the conclusion, and then you enter all of your premises. You don't have to enter all your premises immediately, but it's helpful to do because you can see them all separately. It's easier to see I have these three premises than it is looking at this with the periods and all on the same line. So you want to put in all the premises because you're going to have to use them anyway, and now you can see them. So now that we have all of our premises in, we have our show line, our initial show line, and we have all the premises, now we want to say, can we use our inference rules to get to the conclusion? So if we look at lines 2 and 3, we might think, well, are there any rules that apply to lines 2 and 3? And the first rule we looked at was modus ponens, and so we can ask, does modus ponens apply to lines 2 and 3? The answer is it does. if you have a conditional and it's antecedent, you can apply modus ponens. And what do you get? Well, if we say let's apply to lines 2 and 3 modus ponens, we get the consequent. We get Q. So what you need to do really when you're learning what's most important about, well, you need to know both what the premises and conclusion of an inference rule are, but in particular, you need to know the premises to which the inference rule applies. So here we have the justification for line 5 is 2, 3 modus ponens. Let's check to make sure everything is okay. It still is. So looking good so far. We show line, premises, and then we applied an inference rule. And the syntax for applying inference rules is always the lines to which the inference rule applies, and then the name of the inference rule. If we just said MP, it would say MP has no form with 0 premises. If we said MP23, it would still say MP has no form with 0 premises. That's because we have to put the premises first. So there we go, 2, 3 MP. So at this point, we want to see, are there any other inference rule applications we can make? Well, okay, so we've used 3, we've done modus ponens with it. We're not going to get anything more out of 3. So we want to look at 4 and say, can we get anything out of 4? Well, for modus ponens with line 4, we would need R. Do we have R? No, we don't have R. So there's no modus ponens to be done with line 4. So we want to ask, are there any other applications we can make with 4? Well, so there are 2 rules that work with conditionals. One is MP, and the other is MT. Now think, what does MT require? If you have a conditional, then what's the other premise of MT? It's not the antecedent, it's something to do with the consequent. And what to do with the consequent? The negation of the consequent. So I think, okay, good. We can do MT with lines 4 and 5 because we have not Q on line 4, and there's the consequent without the negation on line 5. So let's try that. 4, 5, MT. Oh, no form of MT is applicable. What's going on? Well, we can click here, and this will give us a little explanation. It says this is the form of MT, and this is what you're trying to do with it. And it says this does not match that. So why not? MT says if you have a conditional and you have the negation of the consequent, then you can infer something. Now here we have a conditional, but we don't have the negation of the consequent. We have the unnegation of the consequent. So our rules are really, really picky. They require that whenever we use them, what we apply them to has to fit the rules exactly. So what we need is not Q, but not Q. Oops, no. Let's try that again. There we go. And now we can do modus tollens with 4 and 6, because 6 is the negation of line 4. And there we have not R. Now, let me make a comment about the pickiness of the rules. There's a reason why we want our rules to be picky. The point of a derivation is that it is a manipulation that's you can check whether or not each of the rules apply without knowing what the symbols mean. It's a purely syntactic or grammatical manipulation that has nothing that in and of itself doesn't say anything about the truth or falsity or the meanings of the symbols. So you know that lines 5 and 6 are equivalent. If you have Q, you can get not Q, and if you have not Q, you can get Q. You understand that because of their meanings. And you know that if 5 is true, then the consequent of 4 is false, and so the antecedent of 4 is false. That's because you understand what negation and the conditional mean. But what we want when we are building a derivation is something that can be evaluated without knowing what the meanings are just by looking at the grammatical rules. And if we say that's what we're going to do, if we're going to look just at the grammatical rules, then indeed, as they're written, 4 and 5 do not let us do modus tollens. You need 4 and 6. And why might you want to do that? Well, there are a whole bunch of reasons. One is you might want to have a computer. Your computer that you're watching this on right now is a logic machine, but it's in some sense, a dumb, stupid logic machine. It's manipulating electronic symbols, but it doesn't understand their meaning. It's able to manipulate the electronic symbols using basically inference rules that are more or less built into the hardware of the computer. So they're useful. Okay, so to return to the specific derivation, we started with showing not R, trying to show not R. We wrote down our 3 premises. We then made some inference rule applications, and we got to not R. Now, hooray, that's good, because not R is what we're trying to show. And that means that we should be done. So how do we tell the program that we're done? Well, what we've done is called a direct derivation. Direct because we actually got to the conclusion. As you'll see, there are other ways to do derivations that don't actually require you to get the conclusion on a line. They're more complicated, and we'll be getting to those in subsequent videos. But this is a direct derivation because we have the conclusion. So we say, on what line do we have the conclusion? Line 7. And then we say DD, and we hit enter. And now two things happen. The show line gets crossed out or canceled, and a box gets placed around all the stuff beneath the show line. So don't worry about what's going on with the box right now. The canceled show line means that we are no longer trying to show it. We have succeeded in showing it. And if we check it, it now says correct derivation. Uniform derivation, don't worry about what that means. Blank line, that's not a problem. What matters is correct and correct. So, good. We have produced a correct derivation with our, in these 4 columns, we have our numbers, our formulas, our justifications, and our comments. So, good. Let's save this and hop back into our slide. So, we're going to have a schematic description of a direct derivation. So on the first line of a direct derivation, we have, in fact, of any derivation, we have show square where square is our conclusion, suppose it's P. And then we have subsequent lines. And on those subsequent lines, we're going to put in premises and some lines are going to be generated as the justification will be premise. The other lines, the justifications will be that the line follows from earlier lines with an inference rule. At some point, we will get P, and at that point, or whatever our conclusion is, and at that point, we're going to cite that line for direct derivation. So we say the line on which P is, so 6, and then we say DD for direct derivation. And that will cancel the initial show line and box the derivation. And as I said, we don't need to worry about why the box is going there right now. The show is, that means we are no longer trying to show it. So we want to review the rules for a derivation. So every derivation starts with a show line for the conclusion. As it happens, you can write any show line anywhere you want. And why is that? Because you're only trying to show the sentence. In the simplest derivation, in the simplest derivations, you only have one show line, the very first line, and in every derivation, the first line is always show the conclusion. You complete the derivation by canceling the show line. That means you've succeeded in showing the sentence you were trying to show. So every derivation ends when you cancel and box the initial show line. And one method to box and cancel, which we've seen, is direct derivation, and you do that by actually getting the show line, by getting the conclusion on a line, and then saying, oh, there is the conclusion on a line. So how do you add lines once you have the initial show line? You can cite a premise, you can apply inference rules, and there are other things that I'll be doing, other things you can do that I'll discuss in subsequent videos. So what you need to remember is that the simplest derivation structure looks like this. You show the conclusion, you enter the premises, you apply inference rules until you get the conclusion on a line, and then you box and cancel with direct derivation. And so I guess we'll take a look at just one more direct derivation to finish this off. And then in subsequent little videos, we will be looking at other more, somewhat more complicated derivation structures. Okay, so here we're going to say, so while this requires no justification, there is nonetheless a shortcut for it. If we write show and then conc for conclusion, the first show line gets automatically entered as showing the conclusion. I'm going to make a comment about it, one more comment about it in a second, but first I want to do the rest of the derivation. So here we have T and if P then Q, and we have not if P then Q. So we want to look to use our conditionals. 3 is the negation of a conditional, and so it can't be the big premise of modus ponens or modus tollens. 2 is a conditional, so we could do modus ponens or modus tollens with it. If we add T, we could infer if P then Q, but we don't have T, so we can't infer if P then Q. Can we do modus tollens? Well, we need the negation of the consequent. And what's the negation of the consequent? Not if P then Q, and that is indeed what we have on line 3. So we can say 2, 3, MT. We have not T, and oh hooray, that is our conclusion. And so we'll say 4DD, and we check it, and it's correct. Now the comment I want to make about this show conclusion is it's not a justification. Show lines have no justification. There's justification for boxing and canceling them, but for writing down a show line, there's no justification because all you're doing is saying you're trying to show that, and you can try to show whatever you want. That's why this is both in quotation marks to indicate that it's not a justification, and it's against a white background. So this is differentiated visually both by being against a white background, not a gray background, and by having parentheses around it, whereas these don't. And that's because it's not a justification, it's just a shortcut command. Okay, good. So that's that. In the next video, we'll do some more sample derivations and also look at some more involved derivation structures, which you will need to learn. So I will see you then.